What is the slope of this graph? How much up and how much over is it going each time? Yes, Molly.
Up 1 over 2.
Let's see. But what does that represent? So she's looking at up 1 over 2. Let's see. If we're talking about up 1, okay, how far apart are those two numbers?
25.
25. And over 2, how far apart are two boxes on the x-axis? If Molly's reading it right and it's up 1 over 2, that's 200. Okay? So you can't just say up 1 over 2. You do have to think about what does that mean in this scenario. Okay? Up 1 is a 25, over 2 is a 200. Let's see what happens when I divide that. 25 divided by 200. Okay, that's going to be 0.13-ish. What does that look like? What does that remind you of? 0.14. So an eyeball estimate is 0.13 with eyeballs. But I bet you it's actually 0.14 because I know that's the rate of change in this situation. Identify x and y intercepts. Where does it cross the x-axis? At 0. Where does it cross the y-axis?
At the origin.
Martine, I need you to stop. Okay, where does it cross the x-axis? Where does it cross the y-axis? X-axis, where does this line hit it?
0.
Y-axis, where does this line hit it? Both of them are 0. X-intercept equals 0. Y-intercept equals 0. Now, you do need to talk about what that means in the problem situation. So let's think about the x-axis. What are these numbers and what are these numbers? Y-axis, that's our dependent quantity. Okay, what do these numbers represent? We missed a stage. We needed to label it. Okay, so these numbers and these numbers. How about these big 1,000 numbers? What does that represent? Kilowatts. This is electricity. You guys have this on your graph? In kilowatt. Okay. And what's the other axis represent? Cost or money in dollars. So if we're saying that x is 0 at the intercept, that's 0 electricity used. Turn off all the lights, unplug everything, no electricity used. Yes?
After you're done explaining some of the stuff, can I go to the bathroom?
Yeah, you can take the path now. So if the x-intercept is 0, that's no electricity used. If the y-axis is 0 and the y-axis is cost, that means no dollars do you owe. No money owed. Your bill is 0. Okay. Determine the cost of a monthly electric bill of 1550 kilowatt hours. How can we figure out what the bill is going to be? Molly?
You would multiply 1,550 by 0.14.
the pattern in our function is that the cost depends on how many kilowatt hours, and if you have a certain number of kilowatt hour, it's 14 cents per kilowatt hour. So just like when we were loading our table, we're going to multiply 1550 times 0.14. 217 is this person's PG&E bill. Determine the amount of electricity used for this bill. Oh, so this time we know the bill. 302 equals what you get when you multiply 0.14 times something.
Divide.
So we're going to have to divide this time. So one time they told us what to put in here for the x. Second time, they told us what to put in here for the function or the y. Here we had to multiply, now we're going to divide. Who can divide that for me? 2,114 kilowatt. Oh, you got something different? Okay, so let's see. 300.02 divided by 0.14. Oh. You guys were all in the right ballpark. 2,143. Maybe that's what you said.
No, I didn't. I said 2,114.
Okay, kilowatt hours. All right. Slopes. I think you know how to do this. If you don't, Mr. Craig and I can walk around. Equations. We might look at those in a minute. I'll come back to those because I know Molly had a specific question farther back. And how far back?
It was the first, like, I need help with it. I don't know how to do it.
Okay, so is it 256? Okay, here we go. Okay. Create an equation, sketch the graph of the function, and it might help most now that you have a calculator. With each given characteristics, use them that are between -10 and 10. It's a smooth curve, continuous, has a minimum,
So it's quadratic.
so they show us that, and is quadratic. You, in your books, are going to maybe need to look back to where we pasted down function families. Let's see where that is. Function families was back on page like 47. Okay, in your books, you have the 4 function families with generic equations and shapes pasted down. So now let's look at the next one down. 11 is done for you. Linear. I'm looking at 12. Linear, discrete, and decreasing. Okay? So linear, discrete, and decreasing. First, we need to create a function, and then we need to make a graph. So if I'm looking back in my book at function families, and I find my group that's linear, okay, here's what we've seen before, okay? And look, I found one that's linear, decreasing, and I know this is discrete. And so I look at kind of the sort of function that I have. I have f of x equals. I have a negative in front of the x. That's going to be important in our function. And this one's plus 3. And you notice this line is up a little off of the, it doesn't cross through 0, 0. It's been raised. That's where this plus 3 comes in. But key characteristics is it has a negative in front of an x, and then it might or might not have something added to it. So here I am, linear. I'm going to say f of x equals negative x. What do you want to add to that equation just to trick it up a little?
2.
Plus 2. Now, I don't know how to make things be discrete on the calculator, but I'm just going to put it into my y equals and realize that I have to chunk it on out. So y equals clear. Negative x plus 2. That's my function. Window. Double check. That looks pretty good. Actually, we were using negative 20, so I'm going to make that negative 10. Positive 10. Scale of 1. Graph. That's my graph. Now I need to sketch it. And it's raised up a little bit, and it's doing this. Okay, so that is linear. It's discrete because instead of drawing a line, I showed isolated points. And it's decreasing. If you're working from left to right, it's going down. But looking in my book helped, and having a calculator helped. Okay, so now let's go ahead and look at number 13. Create an equation that is smooth, increasing, continuous, and exponential. I'll go ahead and look at my function families and say exponential, what did you look like? Here's my exponential page. Okay. This one's decreasing, this one's decreasing, this one's increasing. This one has a whole number 2 in its base. This one has a fraction in the base. So I'm not going to do a fraction because I want it to increase. And one key in exponential functions is that the x is the exponent. All right? So I'm going to create a function, f of x equals, I'm going to just use 3 as the base. What? And I'm going to put my little x up here in the exponent. Now I'm going to go into the calculator clear. I'm going to go y equals, get rid of my last function, 3, raise it to an x. Graph. Oh, good. It took a little while, but there it is. And so now I'm going to sketch it. It starts down here on the x-axis and very quickly loops its way up. It actually goes to infinity in 2 directions. Okay. And again, a whole number right here for the base and an x up there in the exponent. All right. 14. Now that you have your book with your families in front of you and a calculator to help you out, you guys do 14. Mr. Craig and I will walk around.
Yeah, that was the next one.
Okay. We just did 2. This one's wrong.
Which one?
And that one's wrong. I mean, we just did 2, but apparently you're not paying attention. So right now we're working on this one. You might want to check around with your group. What do they have?
Backwards.
That's great, but yours is going down, his is going up. So it's decreasing, it needs to go down.
Yeah, I know I did backwards.
Okay, so this is not right for this. It's linear absolute value. So that's linear. Linear absolute value. Find what those look like here, like around page 50 or so. That looks good. Calculator issues.
Wait, would that one work too?
That works great, but you don't have a function in there. What do you do to do that?
No, I mean like unfortunately.
You could increasing. That's considered decreasing. So.
Yeah.
But is this actually that?
No, it has to be exactly.
Well, does that function represent that graph?
This is freaking. I don't get this.
So?
I really should.
Well, what you need to use, what helps is this calculator and this book. So, what you're on is a linear absolute value. So you gotta find not just linear, but the linear absolute values. And you have random kind of stuff. This is the one to look at. Okay, so look at that one and try and see what is it about its function that makes it do this. This is the kind of graph you need right there. Okay. Here we go, my friends. Hey, this stuff is not easy, okay? But you do need to be putting in effort and paying attention, all right? We just did 2 of them together. Here's the last one. Has a maximum. Continuous linear absolute value. When I look at my packet, linear absolute values with a maximum looks like that. Now I look at functions and see if I can figure out what do I have to do in the function to make it look like that. So if I'm looking right here is one taped down for me, I've got a negative in front of the absolute value of x. Here it's a -2 in front of an absolute value with x plus 2. You can't see that. But both of these are the type that have a maximum, and having a negative out in front is key. Why don't we keep it simple? Negative in front of my absolute value, x plus 1. Most of you did not know that in your brain until you could look back at some of our function families. Now how to sketch that, most of you wouldn't be able to do without this calculator. So y equals clear. To get to absolute value, first of all, I got to put that negative. And the negative is not a subtract. It's this little button down here. Absolute value is something we don't use very much, so it's off in the catalog. I go second, and then I come down here to where it says catalog in blue letters. Its arrow is on absolute, so I push enter. I'm going to put x plus 1. I use spacebar to get out of that absolute value. Graph. There's my graph. Mine has shifted over a tiny bit from the middle. There we go. All right. Looks like we need to practice function families some more. But there were other things that I wanted to look at. Those equations. Let's see. I think we're going to do it in partners. Let's see. Well, maybe at tables. I'm looking at how much time we have left. So, right now.